Hello Math 1093, this is Dr. P with more special angles. Okay, before you go into a panic, recall that special angles, or special angle measures really I should say, are those things like multiples of pi over 3, multiples of pi over 4, multiples of pi over 6, whose sines and cosines I've asked you to learn pretty much from heart. Really using geometry, but mostly from heart at this point. And I'm not going to ask you to do that with these special angles that I present in this video. I'm just doing this video to show that we can actually determine the exact sines and cosines of a few other angle measures on the unit circle. And to do that, we're going to use a couple of formulas called sum of angle and difference of angle identities. Let's write that down. Sum of angle and difference of angle identities. And I'm going to introduce those formulas in this video. I am not going to prove why these formulas are true. We're going to talk about that a little bit in class, I hope. But I do want to present the formulas here. Okay, so here are the formulas. There are basically two of them, although each one splits into two specific formulas. Here's the first one. Sine of alpha plus or minus beta equals sine of alpha cosine of beta plus or minus cosine of alpha sine of beta. And the other one is cosine of alpha plus or minus beta equals cosine of alpha cosine of beta minus or plus sine of alpha sine of beta. Alright, so let me say a bit about how to read these formulas. This first formula, you'll notice it has a plus or minus here, and then a plus or minus here. So, if I want to find the sine of alpha plus beta, I can write that as this formula with a plus here. If I want to find or rewrite sine of alpha minus beta, then I write this formula over on here on the right with a minus here. Similarly, if I want to find cosine of alpha plus beta, now this one's a little bit different because I put minus plus. You've probably never seen a minus plus before. But the idea there is if I want alpha plus beta, or the cosine of that, then I write this formula with a minus here. That is, I take the sign on top. And then if I want cosine of alpha minus beta, then I write this formula with a plus here. Again, not going to say right now why that's true. It takes a little bit of work to prove that using geometry. Instead, we're going to take these as given for now, realizing that there is a way to prove them geometrically, and we're going to use these for now to solve problems. Okay, so now I want to talk about how we might find the sine of 15 degrees. And I realize this goes against my religion of always using radians in these videos, but it's actually a little bit easier to see this if we use degrees. It is possible to do this using radians. It just takes a little more fraction sense. All right, so we've never talked about sine of 15 degrees before, at least I don't think that we have, but I claim that it is possible to find the sine of this angle measure exactly. And the way that we're going to do this is we're going to take this angle measure, 15 degrees, and we're going to relate this to angle measures that we know better. Okay, and the way I'm going to do that specifically here is I'm going to rewrite sine of 15 degrees as the sine of a difference of two angle measures whose sines and cosines I know exactly. Those are 45 degrees and 30 degrees. 45 degrees minus 30 degrees is certainly 15 degrees. So now, in order to find the sine of this, I'm going to use this formula here, sine of alpha minus beta. So I'm going to use this minus sign here, which means I'm going to use the minus sign here. So I want to write down that formula here without doing any substitutions. The formula is sine of alpha cosine of beta minus cosine of alpha sine of beta. Okay, now let's say what alpha and beta are here. Alpha is this angle here, 45 degrees. Beta is 30 degrees. So if I substitute that, then I get sine of 45 degrees cosine of 30 degrees minus cosine of 45 degrees sine of 30 degrees. And now I just need to work out what all those things are. Now remember, because I know the unit circle very well, sine of 45 degrees is root 2 over 2. Cosine of 30 degrees is root 3 over 2. Cosine of 45 degrees is also root 2 over 2. Sine of 30 degrees is exactly 1/2. So if I simplify that, I know that square root of 2 times square root of 3 is the same as square root of 2 times 3. That's root 6. And then multiplying the denominators gives me 4. And then this other product here is square root of 2 over 4. and I can combine those into one fraction and get root 6 minus root 2 over 4. And I claim that that is exactly what sine of 15 degrees is. You can actually check it on your calculator. Your calculator will probably give you a numerical value, not this exact value here. This is a minus sign here. But that numerical value will be equivalent to root 6 minus root 2 over 4. And in fact, this should kind of make sense to us. Like, this should be a sensible answer. Because what is that approximately? Root 6 is somewhere around 2.4. In fact, I'm just going to write down that's approximately 2.4. The square root of 2 is about 1.4. And if I divide that by 4, then I get, that's about 1/4, because the top comes out to 1, and that's 0.25. And if you check the sine of 15 degrees, which I'll do right now, sine of 15 degrees, then I get, oh, look at that, I get 0.2588 approximately. So according to my calculator, sine of 15 degrees is approximately 0.2588. So it's pretty cool. Those come out to be entirely consistent with each other. Okay, let's do one more example just really quickly here to illustrate how we use the sum and difference of angles identities for cosine. All right, so let's try doing a slightly different one now. Let's try doing cosine of, I don't know, let's take 105 degrees. That could be a fun one. I mean, fun by trig standards, I suppose. All right, anyway, cosine of 105 degrees. Now, how am I going to get 105 degrees as a combination of angles that I know about? Well, you may be thinking, well, I know 30 degrees. Heck, I know sine of 15 degrees at this point, which is kind of nice, but I prefer to keep this in angle measures as familiar as possible. Let's see, I know 90 degrees, I know 60 degrees, I know 30 degrees, I know 45 degrees, and then I say, wait a minute. I just said I know 60 degrees and I know 45 degrees, and if I add those together, I get cosine, or I get 105 degrees. So cosine of 105 degrees is going to be cosine of 60 degrees plus 45 degrees. There we go. And now I'm going to use my sum of angles identity for cosine. So I'm going to use these signs here. So this is going to be cosine of alpha, cosine of beta, minus sine of alpha, sine of beta. But what are alpha and beta? Alpha and beta are these two angles here, 60 degrees, 45 degrees. So I get cosine of 60 degrees, cosine of 45 degrees, minus sine of 60 degrees, sine of 45 degrees. And now just substitute those values in. Cosine of 60 degrees is exactly 1/2. Cosine of 45 degrees, root 2 over 2, and then subtract. Sine 60 degrees is root 3 over 2. Sine 45 degrees is root 2 over 2. Simplifying gives me root 2 over 4 minus root 6 over 4. And this time it looks like I'm going to get a value that overall is negative, because root 2 is certainly less than root 6. Now let's just think about that for a minute. Does that make sense? I think that does make sense, because where is this angle located here? 105 degrees. If I draw a coordinate plane, 105 degrees is just a little out past 90 degrees. So if I draw that angle, I should expect its cosine to be negative because it's over here in quadrant 2. And actually, if you were paying attention earlier, you saw that root 6 minus root 2 over 4, that's about 0.25. Well, this is just the opposite of that. That's going to be approximately negative 0.25. Remember, that's an approximation, not the exact value. And really, that should kind of make sense to us, because we're talking about the x-coordinate of this point here. And earlier, when we were working on sine of 15 degrees, we were working on the y-coordinate of a point here at 15 degrees. And it kind of makes sense those should be the same thing. This is about as far out. In fact, it's exactly as far out from the horizontal axis as this one is from the vertical axis. So we should get the opposite value of what we got before. Okay, so anyway, those are examples of how to use the sum and difference of angle identities for sine and cosine. By the way, if you're in my class, you will get these formulas on the test, or some version of them. I might give only the plus version of each and ask you to figure out the minus version. We'll see, but you will get some part of this as a formula that you get to use on the test.